Manned missions to Mars may sound like a distant dream, yet NASA's roadmap already points towards sending humans there by the mid to late 2030s. At first glance, that might feel far away, but in the grand scale of history, it's almost around the corner. The real challenge is not the rocket or the landing, it's something invisible, silent, and far more dangerous: radiation in space. So how dangerous is this radiation both in deep space and on the surface of Mars? And more importantly, what can we actually do about it? Let's find out. Radiation can mean many different things. The light you see right now is radiation. The warmth you feel from a heater is also radiation. These forms are harmless, even essential to life, but for astronauts there are far more dangerous kinds to face. These are the types of radiation that can strip atoms from the body, damage DNA, trigger acute radiation sickness, or in extreme cases cause death. The primary culprit in our solar system is also our life giver, the sun. It constantly emits light across many frequencies and streams, a steady solar wind composed of energized protons, electrons, and alpha particles. Every so often, though the sun erupts with immense power, solar flares and coronal mass ejections eject billions of tons of highly energized particles into space. If an astronaut were caught in the path of one of these events without protection, the results could be devastating. But surprisingly, this isn't even the greatest danger. Even more troubling are galactic cosmic rays particles born from some of the most violent events in the universe, such as supernovae that occurred millions of years ago. These particles range from simple hydrogen nuclei to heavy atomic fragments like uranium stripped of electrons, leaving only their bare nuclei. They travel at nearly the speed of light, piercing through spacecraft shielding and even the human body. Wherever they pass, atoms are ionized, leaving trails of destruction on a microscopic level. On Earth, we rarely think about this danger. That's because we live inside a fortress of natural defenses. Our magnetic field deflects much of the solar wind and guides charged particles toward the poles, creating the beautiful auroras. The magnetic field also prevents the solar wind from stripping away our atmosphere, which itself absorbs most of the galactic cosmic rays that slip through. Together, these protections make Earth an oasis of safety in a hostile universe. But what happens once we step outside this shield? The first major hurdle is the trip itself. A realistic journey to Mars would take at least 100 days. During that entire time, astronauts would be continuously exposed to space radiation. Solar flares and coronal mass ejections can be blocked by the structure of a spacecraft, but the high-energy particles of galactic cosmic radiation, they pass right through. Recent rover missions measured how much radiation an astronaut would absorb during the trip, about 0.66 sievert. That's roughly the same as undergoing a full-body CT scan every 4 to 5 days. Compare that with Earth, where we absorb just 0.0025 sievert in the same period. The best way to block radiation is to put mass in the way, but simply adding thick walls makes a spacecraft too heavy to launch. So what can we do? One tested approach is to create a temporary bunker inside the ship surrounding astronauts with bags of food, water, or supplies during solar events. Another idea is to incorporate water tanks directly into the spacecraft walls, since hydrogen is particularly effective at stopping cosmic rays. Scientists are even exploring futuristic materials such as hydrogenated boron nitride nanotubes. These are incredibly strong, resistant to high temperatures, and rich in hydrogen atoms that could block radiation. In theory, they could line spacesuits or even form the very structure of spacecraft. And then there's the boldest concept, building an artificial magnetic shield, a miniature version of Earth's magnetosphere. This has already been demonstrated on a small scale, but so far the energy demands are too high for real missions. Still, by the 2030s, who knows? Let's imagine we've made it safely to Mars. Is the situation any better on the surface? Unfortunately, not by much. Mars lacks a global magnetic field and its atmosphere is thin. Radiation levels on the ground reach about 0.64 millisieverts per day, already over NASA's acceptable exposure limits. At lower altitudes, protection improves slightly, but not enough to ensure long-term safety. So how can we protect astronauts once they land? One promising plan is to use Martian regolith, the dust and rock covering the planet. Early missions could 3D print habitats from this material, creating thick walls that block radiation. With the mass of Mars itself above them, astronauts would gain natural shielding from solar storms and cosmic rays. And thanks to the fleet of sun-observing spacecraft already in place, astronauts would have advance warnings of dangerous solar events, giving them time to retreat into these shelters. There's no denying that space radiation is one of the greatest obstacles standing between us and interplanetary travel, but solutions are emerging. From advanced materials to underground habitats, each step brings us closer to making deep space missions possible. With enough ingenuity, radiation might be reduced to levels safe enough for humans to live and work beyond Earth's protective shield. And if that happens, then perhaps the dream of long-term human exploration and even colonization of the solar system could finally begin. But here's the question for you. Do you think humanity will truly overcome the challenge of space radiation, or is this barrier simply too great to cross? Thank you for joining us on this journey. If you enjoyed exploring this question, be sure to check out more from Cosmic Compass. Your support, whether by liking, sharing or subscribing, helps us keep bringing these stories to life. Until next time, let's keep reaching for the stars.